Good morning and happy Tuesday, everyone. I hope you all had a great weekend. Today's problem involves solving the accelerations and tensions of a double Atwood machine. There's a lot of parts here, but some of them are actually solved pretty quickly, so we're in luck. Before we begin with part A, I think it's important to get a visualization of how this machine even works. I've set things up such that once we release the machine from rest, blocks 1 and 2 and pulley B will move downward, and in response, block 3 will move upward, like this. Let's keep that movement in mind as we draw our free body diagrams. Our objects will have nearly identical setups here, so let's do them all on the same slide at once. If we remove their labels and we add our axes, we can start adding some vectors. The blocks will all have their weights pointing straight down and their tensions pointing upward. I've drawn the weight vectors for block 1 and 2 longer than their tensions since the net motion is down, and vice versa for block 3. For pulley B, we weren't provided a mass, so we can't draw a weight vector here, but we certainly can draw the tension vectors acting on this object. Let's draw some acceleration vectors here as well. For blocks 1 and 2, as well as pulley B, there will be a net acceleration pointing down and a net acceleration pointing up for block 3. And that's all of the vectors that we need to include here. Let's move on to the sum of forces acting on these objects. We can save some time here by ignoring the sums in the x direction since all the movement is vertical. Here I've applied Newton's second law to the blocks, which give us these very simple expressions. We can't use that on pulley B, however. The best we can do there is to apply the sum of tensions acting on it while it's initially at rest, which is what I've done in this line here. All of this is helpful, but unfortunately we're in a bit of trouble. We have 4 equations, but 6 unknowns. 3 in the form of the block accelerations, 2 in the form of the string tensions, as well as the pulley's acceleration, which we don't know either. So what are we supposed to do? Here's what I would recommend. Let's go back to our picture and focus specifically on string C. If we draw a reference line at the top of pulley B like this, it's possible to get the length of this entire string. I'll draw the distance from that reference line down to pulley B on the left, as well as the distance to block 3 from that reference line over on the right. If we add these two distances together, well, that's our length of string C. It might not seem very useful, but check this out. I'll take a derivative of both sides with respect to time, which gives me this velocity relation. The right-hand side becomes 0 because the length of the string doesn't change once the masses begin to move. If we do this derivative again, we end up with an identical acceleration expression. By moving the acceleration of block 3 over to the right-hand side, we see that the accelerations of pulley B and block 3 are negatives of one another. This agrees with what we saw in the picture earlier. We still need one more equation, though. Let's take a look at string A next. It's the same idea here. We'll put a reference line in the same spot, and then draw the distance from that line to block 1 on the left and block 2 on the right. But we need to be careful here, though, since we're overshooting the distance in x1 and x2 by the distance from the reference line down to pulley B. We don't want that in our expressions. Thus, we'll have to subtract that quantity from both of those in our equation representing the length of string A, like this. With that taken care of, we can do the same process as before and take a derivative with respect to time on both sides. We'll get another velocity relation that's equal to 0 since the length of string A doesn't change in time either. There's two negative velocity terms for pulley B here, one here and one here, so let's collect them before moving forward. If we do this process again and apply another derivative, we'll end up with a rather interesting equation for the acceleration. If we move the acceleration term for pulley B over to the right and then divide both sides by 2, well, this says that the acceleration of pulley B is the average of the accelerations for block 1 and block 2. Interesting. Now we have 6 equations and we can proceed. Here's all of them on one slide with some reference numbers so that we can easily grab them for substitutions later. Now we can finally begin part A. Let's get started and grab equation number 6. We need to find some substitutions for the accelerations of block 1 and block 2, so let's try these. In equation 1 and 2, I'm going to divide these expressions by their respective masses, which will give us these results here. Let's plug those back into the equation that we're working on up here. The inner set of parentheses is just meant to separate the left-hand sides of A1 and A2 that we just inserted. They aren't really necessary anymore, so let's go ahead and get rid of those. We can collect the like terms of G and factor out a negative tension of string A from both of these ratios involving mass. We'll need another equation to eliminate this tension variable, so let's try this one. I'll move the tension of string C over to the right and then divide both sides by 2. And here is what we can replace the tension in string A with. This expression right here. When we do that, it might not seem like we really did much, since we just replaced one tension with another, but we can use equation number 3 to get rid of the tension altogether. I'll isolate the tension of string C on the right, then factor out the mass of block 3 on the left to make it look nice. Now we have a replacement for that tension. There's a lot of parentheses going on here now, so let's distribute the outermost coefficient of -1/2 inside here to get rid of a pair of those parentheses. I'll pull in the 1/2 first, then the negative, which switches the sign of our terms. There's a lot of different denominators going on here as well, so let's work on that and focus on the mass ratios inside these parentheses first. I'll multiply both of those ratios by a special form of 1 so we can get a common denominator. This will alter their forms and allow us to collect them together, like this. With those fixed, we can break up the coefficient out front into a difference of ratios. The idea here is to FOIL this expression into 4 terms that all have common denominators. Notice that 2 of these terms here contain the acceleration of block 3, which belongs on the right-hand side, not the left. Let's move those 2 over, like this. Next, we can factor out the acceleration of block 3 from everything on the right. I want to ultimately divide things out so that the acceleration of block 3 is by itself on the right-hand side, but that's not possible yet since this G term here and this one term here don't have a common denominator with everything else. Let's fix that up by multiplying both of those by a special form of 1. If we incorporate that, here's where we stand. Let's also factor out g on the left-hand side, because there's a g here, and a g here, so we don't need to keep it in every single term. There's a common denominator on both sides now, so let's go ahead and divide both sides by everything in the parentheses here on the right. The result looks nasty, but we're in luck. Since the denominators are the same upstairs as well as downstairs, well, they'll cancel out and we don't have to worry about them. In the end, we will finally get our result for the acceleration of block 3. And that's it. Part A is done. Part B is a quick one, thanks to this previous equation that we had figured out earlier. If we take our expression for the acceleration of block 3 and slap a negative out front, that's all that's needed to rebrand it as the acceleration of Pulley D. And we're done. That's it. On to part C. Let's start this one with equation number 1. All we want is the acceleration on the right-hand side, this one, so let's divide both sides by the mass of this block. We can use the same strategy as before to get the tension of string A removed by grabbing our previous result from equation 4. When we insert it, here's where we're at. We need to get rid of the tension in string C again, so let's use equation number 3 one more time to get a replacement. Remember that we isolated the tension on the right, and then factored out the mass on the left. Let's get that switched out. Since we figured out the expression for the acceleration of block 3, we can also plug that in here as well. It's not too pretty, but we can take a couple minutes to get that all fixed up. Let's do the easy stuff first. I'll factor out g from both terms here inside these parentheses. Next, we can multiply this 1 by a special form of 1 to get a common denominator going on there. With that added, we can just use a single ratio here and get rid of those innermost parentheses. Notice there is a positive and a negative version of m1, m3, okay, positive here, negative here, as well as m2, m3, positive here, negative here. So when we combine like terms, those will cancel out, and we're left with adding the first term and the last term. That gives us a total of 8 times m1, m2 in the numerator. Let's simplify things a bit and get rid of some parts of the coefficient hanging on to these remaining parentheses. We have an m1 in the denominator here and then 1 in the numerator here, so those will cancel out, and the 2 in this denominator will reduce our 8 down to a 4. We can also bring this m3 inside the parentheses as well, like this. Again, we need a common denominator to sum both of these things together. So let's go ahead and multiply that first g term by a special form of 1 to make that work out. There's a g in both terms here that can be factored, and since we have common denominators now, we can write everything as a single ratio. If we collect like terms, we'll end up with the following result for the acceleration of block 1. And part C is now complete. One more acceleration to deal with. If we grab equation number 6 again, we can do a little algebra to get the acceleration of block 2 isolated. Let's multiply both sides by -1 as well as 2 then subtract the acceleration of block 1 on both sides. Both of the accelerations on the right here we have expressions for, so we're free to insert those. Thankfully, they both have common denominators already, so we don't have to do that business all over again. Let's distribute this -2 into the numerator of this first chunk. Then we can factor out g from both terms and write everything using a single ratio. After adding like terms, here's the result. That's all we needed to do for part D. Next up is the tension in string A. We have equation number 1 here again, and what we should do is switch the tension term with MA to isolate it on the right. We know what the acceleration of block number 1 is, so let's just put that in there. There's really no need for an extra set of inner parentheses here, so we can factor this inner g out to get rid of a pair of those. Let's get a common denominator for m1g going on by multiplying this term by a special form of 1, which allows us to distribute m1 into both terms like this. It looks a little strange with some squared masses going on, but those will go away in just a moment. Let's factor these g's out, like we've done a couple times already, and use a single ratio, like before. When we add like terms, the only thing that's remaining in the numerator is a term containing all 3 masses. And that's it. We're good to go here. What about the tension in string C? Well, that's actually another really easy part too, thanks to this equation from earlier. All we have to do is take our result for the tension in string A and multiply it by 2, and that's it. Tension C is now complete as well. There is one last thing we need to do, however, and that's to evaluate the behavior of our double Atwood machine with a special case of the blocks. We can set them up in such a way such that everything should balance perfectly and we shouldn't have any accelerations occurring. Let's see if our results can achieve that. Here in the upper left corner, I've provided the new definitions where m1 and m2 are equal, so we can just call both of them m, and m3 is 2 times m. Let's start with the acceleration of block 1. If we plug in the new definitions, multiply, then add like terms, we'll end up with a 0 in the numerator, which collapses the whole thing down to 0. Cool. Next is the acceleration of block 2. Same process. Plug in, multiply, and add like terms. A 0 in the numerator means 0 for the whole thing. Looking good so far. Next is the acceleration of block 3. Plug in, multiply, add like terms, and we get 0, just like the other two. What's great about this result here is that we actually get 2 answers for the work of 1. Recall that the acceleration of pulley B is the negative of the acceleration of block 3, and the negative of 0 is just 0. So all that's left are the tensions. Let's do them alphabetically, starting with A. Like the others before, insert the new definitions and multiply, but we don't end up with 0 here. Let's simplify the denominator as well with the same process. If we insert, multiply, and add like terms downstairs, everything cancels out except for a single portion of mg. Well, this would mean that the tension in string C better reduce to 2 times mg. Let's see what we get. Insert, multiply, and here's our numerator. Then do the same for the denominator. What do we get? Well, when we reduce, 2 mg, as expected. I'll bring all of those results together on another slide so we can see them all at once. And just as we anticipated, all of the accelerations go to 0, and the tensions reduce to the appropriate amounts in regards to these new mass definitions. Everything is in equilibrium. And we're done. Thanks for watching, everyone. Have a great day, and I'll see you in the next problem.